Okay, now we're gonna draw another molecule and we're gonna determine what hydrogens are more acidic using this tool. So again, let's first draw the structure, and our strategy will be starting from the acid, draw the conjugate bases. So this is my molecule, and I'm gonna call that, I'm gonna give it names. That's a chlorine here, and here I have hydrogen A, double bond, and now I have this. Let's see. This molecule has multiple places, multiple hydrogens that we're going to be determining the strength of the acid, of the different hydrogens. And here I have two hydrogens. Oh, I am missing a bond, but never mind, we are going to fix it. So, and I am going to add, one more bond. Because my point is, I want to add a hydrogen. Okay, now that I have that, I have A, B, C, D, E, all of those hydrogens. So to assess the acidity of those, I'm going to just do it differently, not drawing everything, because we did it before. So strategy-wise, draw the molecule, draw the conjugate bases by removing each of the hydrogens. So I am removing, say, notice we're going to do the first part of the molecule, and I'm going to use a strategy that simplifies my drawing. I'm going to call that R, everything, this part of the molecule, and I'm going to analyze just this part where hydrogens A and B are. B, oh, all right. So it is the same, only that I have given these R is all of this part below. Now I notice here, hydrogen, this is on an oxygen, this is on an oxygen. So those two are carboxylic acids. When I remove any of the hydrogens, say that I remove this, I am creating this anion, which I can stabilize by resonance. The same thing here. I have resonance effects. Turns out that atom is the same. I have the same resonance effects. But now, let's put the hydrogen back. And we're going to analyze not to have so many things in here. And we're going to look at what is different then. If the atom is the same and resonance is the same, now let's look at the next effect, which is induction. I see that here I have a chlorine. And the chlorine here, notice, is right next to here the carbon that has, we call that a carbonyl, right next to that. And on the other side, what we have is one carbon in between. So notice that it's farther away. So it's not right next to it, but there is an intermediate. There is a carbon there. So the chlorine is closer to this than it is to the other side. That means that when I form my anion here, the anion is not only going to be able, is stabilized by resonance, but also you have the electron withdrawing effect of the chlorine, which is closer here than it is to that side. So closer, chlorine is closer for H in HB. That means right there, notice here in between these two, I'm going to say then that hydrogen B are more acidic than hydrogen in A. I did that analysis. Now, moving on to the other atoms, if I check this out, notice that removing that electron, proton in E, if I did that, and I'm going to do it now, I am creating this conjugate base. And here charge is on an oxygen. Comparing that, but here I don't have, atom is the same, but I don't have any resonance effect. So right there, this is less acidic than this two because hydrogens A and B, we had resonance. So I'm gonna put that hydrogen back. And now I can keep ranking that. That was E. So keeping my ranking, I'm gonna say HB is more acidic than HA, and that is more acidic than H, that was an E. E. Okay, that. Then I am analyzing hydrogens D and C. When let's say that I remove this one. If I remove hydrogen C, I'm gonna have this. If I did it, notice that here, these electrons, the carbon is sp hybridized. So the pair of electrons are on an sp orbital. And if I remove the hydrogen here, the carbon is sp3 hybridized. So bottom line, and put in my hydrogen back. So if this was C, if by removing that is on an sp orbital, that bond, so that that bond here is the carbon is sp hybridized. Therefore, the lone pair is going to be on an sp orbital. Conversely, if I remove this hydrogen, then the conjugate base, and we can see it by removing this one. Now, here's my lone pair, and it's going to be on an sp3 orbital. So I'm looking at that effect now. In this two, the charge resides on a carbon, so atom is the same. I don't have resonance effect. Actually, this is localized. The charge here will also be localized, so no resonance effect, no inductive effect, but orbital. So I don't have that, I don't have that. Atom is the same, but the orbital here is sp3, and here in which the charge resides, and here is sp. Remember that sp are closer to the nucleus because this is 50% S, 50% P, and this is 25% S only, so larger orbitals. Therefore, charge on an sp is more stable. And right there we have then determined that hydrogen C is more acidic than hydrogen D, which I'm drawing back, HD. So about the three were the strongest acid. In continuing the ranking, the other two charge was on a carbon, but bottom line, hydrogen, the charge here will reside on an sp orbital, and in the other, this is the least acidic because charge is on a sp3 orbital. So that is the ranking, more acidic to least acidic in this molecule.